Hi everybody. So in today's video, we're going to be going through the 1.2 task notes and kind of practicing some of the following learning targets. The first one is I can identify if a sequence is arithmetic or geometric and support my reasoning. So identify means we need to just be able to use the vocabulary and decide between arithmetic and geometric. Supporting my reasoning means explaining how I know my answer. The second learning target is I can identify the common difference or common ratio in an arithmetic or geometric sequence and interpret in the context of the problem. I'm going to be honest with you, we're not going to work on the interpreting today. It's just going to be about identifying. That's the part we're going to focus on, is finding the common difference or common ratio. The other thing we're going to work on is I can evaluate, which means find the value of linear and exponential expressions. And finally, we are going to work on writing equivalent forms, which means writing it in a new way that means the same thing, of exponential relations. So let's start by talking about graphs. We're going to be starting with looking at two separate graphs here. The first one is the graph that looks like this, and the second one is the graph that looks like this. From these graphs, we need to know how to turn our information into a table of values. So let's start with that. When we make a table, just like in our previous video, we need to have labels. So in our previous video, we said the left-hand column should be the x-axis of the table. In this case, that means that we're going to label this left-hand column the figure number. Now we also need to have a label for our right-hand column, which is going to be the y-axis of the table. So in this case, it says number of squares. So I'm just going to fill that in as the label on my table. Now, in our previous video, we started with numbers in our table and we graphed them. What we're going to do in this video is we're going to start with a graph and translate those values to the table. So let's start with the first point. For this point right here, the x number is 0 and the y number is 10. For the next point, the x number is 1 and the y number is 8. For the next point, the x number is 2 and the y number is 6. Then we have an x number of 3 and a y number of 4. And finally, we have an x number of 4 and a y number of 2. Okay, now that we've practiced making a table by using a graph, let's try to describe the sequence using vocabulary. As a reminder, an arithmetic sequence is going to be when we have an adding or subtracting pattern in our table, and a geometric sequence is when we have a multiplying or dividing pattern in our table. So in order to figure out what type of sequence we have, we could start by looking at the table. In this table, I can see that in the y column, the pattern seems to be that we are subtracting 2 each time as we move down the table. So 10 minus 2 is 8, 8 minus 2 is 6, 6 minus 2 is 4, 4 minus 2 is 0. We can also see that on the graph looks like a line. If I were to connect those dots, they would be in a straight line. Based on both of those pieces of information, I can say that this sequence is arithmetic. And I could explain this in several different ways. Using the graph, I could say that the graph looks like a line. That's the first option for explaining. The second option for explaining is that the pattern is subtracting 2 each time. Now, it's really important that we say these words each time. And the reason we need to say that is it matters that we're doing it the same pattern over and over again. For example, if the first number was subtracting 2 to get to the next number, but then we needed to subtract 3, that would no longer be arithmetic. We need to be subtracting or adding the same number every time. Now, based on this information, we need to decide if our pattern has a common difference or a common ratio. Whenever your sequence is arithmetic, we are always going to say that we have a common difference. These two things are tied together. Arithmetic and common difference go together. Geometric and common ratio go together. If we have a common difference, then this pattern is the common difference. So we would say that our value is -2 because that's what we're subtracting every time. Now let's look at a different kind of graph. Right away, you should notice that this graph looks different. The dots are no longer in a straight line. And as a matter of fact, this graph is what we would call a curve. So because this graph is a curve, it tells me it's a different type of pattern. Now, before we answer these questions, let's take a second and just practice making a table. Just like in our previous problem, a table needs to have labels. So the x-axis label needs to be the first column in our table, which means we would label this figure number. The y-axis label needs to be the second column in our table, which means we would label this number of dots. Now, if we want to translate these points on the graph to the table, this first point here has an x-coordinate of 0 and a y-coordinate of 1. 0 on the x, 1 on the y. This next point has an x-coordinate of 1 and a y-coordinate of 2. The next point has an x-coordinate of 2 and a y-coordinate of 4. And the last point has an x-coordinate of 3 and a y-coordinate of 8. Now, just like the fact that this graph was curved told me that this is a different kind of pattern, I can see that same pattern in the table. Instead of adding or subtracting the same number every time here, to follow this pattern, I would need to use multiplication. Multiply by 2, multiply by 2, and multiply by 2. This tells me, for two reasons, the fact that the graph is a curve and the fact that there's a multiplication pattern, that this is a geometric sequence. Now again, if this was multiply by 2 and then multiply by 3, we would say neither. It would be neither of those options. We have two different ways to explain our reasoning here. We could say that the graph looks like a curve. We could also say that the pattern is, instead of subtracting 2, we are multiplying by 2 each time. And again, this phrase each time is really important because it needs to be a consistent pattern that happens every time in order for this to be a geometric sequence. Now, just like up here, we said that arithmetic sequence automatically goes with common difference, geometric sequence automatically goes with common ratio. And your common ratio is what are you multiplying by? So we would say we are multiplying by 2 each time. Now let's go ahead and compare some tables. So just like in the previous problem where we gave you two graphs and we had you change them to a table and talk about them, here I'm going to give you two tables. I'm going to have you make graphs and then talk about them using vocabulary. So let's practice taking a table and making a graph. As we've discussed, this first column is the label that I'm going to put on the x-axis. So I would write figure number down here at the bottom. And that's going to be my x-axis. And I would write for my y-axis the right side column, which in this case is going to be number of boxes. Now on my x-axis, my values need to be 1, 2, 3, and 4. So I'm going to label those 1, 2, 3, and 4. And on my y-axis, my biggest number is 9. So what I'm going to do here is just count my lines, 1, 2, 3, 4, 5, 6, 7, 8, 9. It seems like by counting by 1, I can get to 9. So I'm going to have 1, 2, 3, 4, 5, 6, 7, 8, 9. Now I'm going to graph my points. So when the x is 1, the y is 3. When the x is 2, the y is 5. When the x is 3, the y is 7. And when the x is 4, the y is 9. Now, right away here, I can see a couple different ways to decide if this is an arithmetic or a geometric sequence. The first thing that I'm noticing is that this graph looks like a line, which tells me that this is an arithmetic sequence. The second thing that I'm noticing is that my pattern in my table is that I'm adding 2 each time. So because I'm adding 2, that's an addition pattern that's consistent. I'm going to use arithmetic to describe this sequence. And I could justify my reasoning in 2 different ways. I could say the pattern is adding 2 each time. And again, those words each time are really important because it means we're doing it over and over and over again. I could also say that the graph looks like a line. Now, just like before, arithmetic is connected to common difference. So as soon as you say arithmetic, you know it's a common difference. Common difference means what is the number I'm adding or subtracting each time. In this case, the value would be plus 2. I could also see that pattern on my table by looking here at the distance between the points. They're going up by 2 each time. Now let's consider the following table. Now this table is a little bit different. We've got some really big numbers here, but I don't want to panic. It's going to be okay. Just like before, we're going to label our x and our y axis for our graph. So figure number is going to go on the x. Because that's the first column in my table. And number of boxes is going to go on the y because that's the second column in my table. Now, my x-axis is pretty easy to label. I only need the numbers 1, 2, 3, and 4. My y-axis is a little bit trickier because my biggest number here is actually over 1,000. It's 1,250. Now, I've only got 10 lines here, so my thinking is I should probably count by a bigger number, something like maybe 200. I'm imagining if I count by 20, it would be 20, 40, 60, 80, 100, 120, 140, 160, 180, 200. 200 might be better. 200, 400, 600, 800, 1,000. That seems to get me a little bit closer to 1,250. So I would maybe count by 200. 200, 400, 600, 800, 1,000, 1,200, 1,400, 1,600, 1,800, 2,000. Now you could try counting by something smaller, like maybe 150. 200 seems like a pretty easy number to count by, so that's why I'm going to go with it. Now the first point is going to be 1 and then 1,250, so a little bit above the 1,200. Then I'm going to have 2 and 250, so a little bit above the 200. 3 and 50, so a little bit above the bottom. 4 and 10, so really close to the bottom. Right away, I'm noticing that this graph is not a line anymore. It looks more like a curve. And because this graph looks like a curve, it's giving me the idea that it's probably a geometric sequence. Now, if I look at the table, the numbers seem to be getting smaller. So instead of multiplying here, I'm guessing I'm probably dividing. For example, 50 divided by 5 would give me 10. 250 divided by 5 would give me 50. and 1250 divided by 5 would give me 250. You can always check those numbers on a calculator if you want to make sure, but I'm going to tell you it definitely is dividing by 5 each time. So to describe my sequence here, the first thing I would notice is that it's a geometric sequence, and I can describe and explain my reasoning in two ways. I could say the pattern is dividing by 5 each time. And again, those words each time are really important to show that you're doing the same pattern over and over again. I could also say that the graph looks like a curve. Now, as soon as I've chosen this is a geometric and determined it was a geometric sequence, I'm going to know that I have a common ratio. Here's where geometric gets a little tricky. For your value here, you cannot use division. There's no division allowed when we talk about the common ratio. It always has to be multiplication. So one of the things we need to do is we need to convert division to multiplication. In this case, dividing by 5 can be converted to multiplying by 1/5. You just take whatever number you're dividing by and put it in the bottom of a fraction and the number 1 on the top. As a follow-up example, just as a follow-up, dividing by 3 would change to multiplying by 1/3 because division is illegal when it comes to writing the common ratio. So because of that, instead of putting dividing by 5 here, I would put that my common ratio is 1/5. Okay, now that we've talked about and practiced looking at a table, looking at a graph, and using some vocabulary to describe it, I'd like to go through some information that we need to know about exponents, because exponents are one of the things coming up in the future videos that we're going to use a lot to describe our patterns. An exponent shows that we are multiplying repeatedly. So you can imagine if we're going to have patterns where we multiply over and over again, we're going to use exponents to describe them. For example, 4 to the third power tells me to put the number 4 3 times with multiplication between them. And I know that there should be 3 copies of the number 4 because the exponent was a 3. Now, using this idea, one of the things that we're going to ask you to do is to write out what's called expanded form of exponential notation. So kind of write it out the long way like we did here. For example, I might show you something like this and say, write it out the long way. The first thing that we should know is that the exponent only goes with the 5 because that is inside of the parentheses with the 5 and the 2 is on the outside. So what that tells me is that when I write this out in expanded form, I'm only going to write down the number 2 one time. And then I'm going to put down 4 copies of the number 5. And the reason I know to put 4 copies of the number 5 is because the exponent here is a 4. In the next example, we have -7 to the third power, and you'll notice that the exponent says we want 3 copies of this whole thing, this parentheses -7. So I would literally write parentheses -7 times parentheses -7 times parentheses -7 because we want 3 copies of that in multiplication. Now here's where it's important to pay attention to the details. This problem had a parentheses, so we wrote 3 copies of this entire thing, -7. You'll notice that this problem does not have a parentheses. What that means is that the 3 only applies to the 7, not to the negative. So to write this out the long way, I would only put down the negative 1 time. Then I would write 3 copies of just 7. So the exponent still tells me how many copies to make. It's not making copies of the negative. It's only making copies of the 7. Last but not least, we have 2x to the fourth. Now, the tricky thing here is that a lot of students think that this means 2x times 2x times 2x times 2x. But really, this fourth power only applies to the x because that's what's right next to it. The 2 is considered separate from the exponent. So to write this out in the expanded form, I would write the 2 down 1 time, and then I would write the x 4 times with multiplication symbols in between. And the reason I'm writing 4 of them is because the exponent here was a 4. All right, thank you everybody so much for watching, and I look forward to seeing you soon. Oh my gosh, I almost forgot that there's actually one more part to these notes. So in this part of the notes, we're going to introduce you to a specific notation that we're going to use when it comes to describing the relationship between inputs and outputs. So if we look at the following table, the first thing is, can we answer these questions using the table? If I asked you how many dots were there in figure number 3, and then justify your answer, we would use the table to figure this out. If I'm looking for figure number 3, then in the figure number column, I would find the number 3 and match it up to however many dots that says. So what that means is that I would say there are 11 dots in figure 3 because when the input is 3, the output is 11. Now, that should seem pretty straightforward, but one of the things that we're going to talk about is that there's actually a faster way to write this, because this is a lot of words to describe an input and an output. So we're going to talk about something called function notation. Your friend tells you she just learned about the function notation, and she writes an example of the function notation that talks about the relationship between dots and figure number. She says d of 2 is equal to 8. In order to understand this notation, it's going to be really helpful to think about where else we see a 2 and an 8. If we look in the table, we should notice that when the input is 2, the output is 8. And that's the same thing we're seeing here. When the input is 2, the output is 8. Now, what does the D mean? Well, if you remember, if we think back to the table, we are talking about the number of dots, which we could use the letter D to stand for, because D stands for dots. This D right here just tells us that the function we're using is talking about the number of dots. So if I were going to read this notation out loud, I would say the number of dots after 2 figures is 8. What do you notice about function notation and the table? What we really want you to notice here is that function notation is just a faster way to communicate the relationship between inputs and outputs without having to write so many words each time the way that we did in this sentence up here. So let's take this entire table and write it in function notation. Since we're counting the number of dots, for this first relationship, 1 and 5, we could say the number of dots in figure 1, and you'll notice that the 1 is the input, is equal to 5, which is the number in the output column. For the second relationship, we could say the number of dots for figure 2 is equal to 8. The inputs always go inside the parentheses and the outputs are always on the outside. The variable or the letter that we're using to stand for outputs is also on the outside. You'll see D is on the outside, the outputs are on the outside. We could say the number of dots in figure 3 is equal to 11. And we could say the number of dots in figure 4 is equal to 14. This means the same thing as what we've communicated in the table. All of the inputs are in this first column. Inside of the parentheses. All of the outputs are outside of the parentheses. After the equal sign. And the variable that represents the outputs is the variable that we use at the beginning. Now, this all together is what's called function notation. Function notation just gives you the input and the output of a function. So this letter on the outside here is always the output variable. In this case, in the example above, we use the letter D because we were counting the number of dots. Inside of the parentheses is always the input number. And after the equal sign is always the output number. The inputs are always the x values of the function, and the outputs are always the y values of the function. So what do you think someone would be asking you to do if they said find d of 4? If a problem says find d of 4, what that means is find the output. In this case, we're using the variable d, when the input is 4, which is inside the parentheses. So your answer would look like this. D of 4 is equal to, now based on the table, I can say that that is 14, because when the input is 4, the output is 14, and that would be your answer. All right, now we're officially done. Thank you guys again for watching, and I'll see you soon.